This content is produced by PASS, the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials, so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. A manufactured roof truss is not a rafter with extra pieces nailed into it. It is a complete engineered load path. That single distinction controls almost every supervision decision in this lesson. If somebody cuts a web, drills a cord, moves a connector, or hangs an unverified load from the truss, the question is not whether the cut looks small. The question is whether the approved structural system still works as designed. I want you to carry one field rule from the first minute to the last. Drawings first, brace as you go, and keep every saw and drill off the truss unless written engineering approval says otherwise. That rule is simple enough to use during layout, rough mechanical work, framing inspection, and closeout. It also separates manufactured trusses from conventional solid sawn framing, where limited boring or notching may be permitted under specific rules. The central reason is load path. A truss gets its efficiency from the way its top cord, bottom cord, web members, and metal connector plates work together. The top and bottom do not act like independent boards. The triangles move forces through the whole assembly. A small field alteration can change where those forces travel, and the person holding the saw cannot verify the new force path by eye. I sometimes compare a truss to a tight net. A solid board has wood through its whole depth. A truss uses separated pieces arranged so tension and compression can pass through a specific geometry. Cut one important strand in a tight net, and the surrounding strands have to pick up work they were not arranged to carry. That comparison is not a design calculation, but it helps explain why the ordinary carpenter's instinct to patch, sister, or add a scrap gusset is not enough. The California Building Code and the California Residential Code set a clear boundary. Truss members and components cannot be cut, notched, drilled, spliced, or otherwise altered without written concurrence and approval from a registered design professional. The Commercial Code reference is Section 303.4.5. The residential reference is Section R802.10.4. I want to be precise about what that means in the field. The rule applies to every trade. An electrician does not get a small hole exception through a truss web. A plumbing crew does not get to notch a cord because the vent is close. A heating and cooling subcontractor does not get to trim a diagonal member to straighten a duct run. The issue is not which trade has the harder route. The issue is that the truss was engineered before any of those field cuts existed. Imagine a mechanical subcontractor who discovers that a rigid duct wants to pass through a diagonal web. The tempting move is to make the opening and fix the wood afterward. The correct supervision move is to stop the proposed alteration, compare the conflict with the approved truss documents, and route the issue to the truss manufacturer or a registered design professional. The route may change, or a written repair or modification detail may be issued. Until that happens, the truss stays uncut. I use a plain memory connection here. If it has a metal plate, the other trades wait. That is not a substitute for reading the documents, and not every plated item is identical, but it is a useful job site pause button. It reminds the crew that a manufactured truss is not an open invitation for conventional boring and notching rules. The next supervision question is whether the correct truss package is actually on the job. California Building Code, Section 2303.4.1.1 requires the truss design drawings to be provided to the building official for approval before installation. Those drawings must also be provided with the shipment delivered to the job site. That requirement matters because the architectural roof plan does not contain every piece of truss-specific information. The truss design drawings identify the engineered truss and include the design information needed for fabrication and installation. The placement information tells the framing team where each marked truss belongs. The package can also carry bearing information, restraint locations, and other details that control installation. I put a reference table on screen that separates the main documents and field decisions. The approved truss design drawings control the individual truss. The placement information controls where the truss goes. A written repair or modification detail controls what may happen after damage or an approved change. If the package is missing, the truss marks do not match, or a field condition conflicts with the approved layout, I do not solve that conflict by improvising with the crane waiting. A disciplined receiving check starts with identity. I compare the shipment marks with the approved package. I confirm that the truss types, orientation, bearing locations, and specified restraints line up with the planned installation. I also make sure the documents are available for the people who need them, including the building official and any special inspector whose work is triggered. Shop drawings are not decorative paperwork that can stay in a trailer under a stack of invoices. They are part of the construction control system. They connect design, delivery, erection, inspection, and any later repair. When the documents are treated as an afterthought, the crew can install the correct-looking truss in the wrong location, or miss a restraint note that is invisible after the roof is closed. The practical field distinction is easy to remember. Plans tell you the intended building. Approved truss documents tell you how the manufactured truss package is designed and placed within that building. I use both. I do not let one silently replace the other. The truss package can be correct, and the delivered material can still be damaged. The source-backed inspection duty is straightforward. Trusses should be examined on delivery and after erection for cracked members, dislodged connector plates, or other damage that impairs structural integrity. I look before the crane starts creating schedule pressure. A cracked cord, a split web, or a connector plate that is pulled away from the wood is not a cosmetic item. I identify the truss, protect it from being installed as though it were sound, and obtain the required written repair direction. The repair comes from a registered design professional, often coordinated through the truss manufacturer. It does not come from the quickest field idea. That authority line is important. A building inspector can require compliance and review the resulting work, but the inspector is not the person who invents the structural repair. The general B contractor also does not gain repair design authority from years of good framing experience. Experience helps me recognize the problem early. Engineering authority determines the repair. Suppose a forklift cracks the bottom cord during unloading. A crew might suggest plywood on both sides, adhesive, and a row of fasteners because that has worked on other wood repairs. The problem is that the crew does not know the cord force, the connector demand, the required repair length, or the fastening schedule for that truss. The correct path is written repair design, exact installation of that design, and required inspection before concealment. I also separate damage from alteration. Damage may be accidental, alteration may be intentional. The response is still controlled by the same boundary. Do not guess at the structural fix. The most vulnerable part of many truss jobs is not the finished roof. It is the erection period, when tall, narrow members are standing before the full restraint system and sheathing are complete. A truss can be strong under the vertical loads it was designed to carry and still be unstable from side to side while it is being placed. California Division of Occupational Safety and Health Rules in Title 8, Section 17, 09 subsection B require trusses and beams to be braced laterally and progressively during construction to prevent buckling or overturning. Progressive means the stability work advances with the erection. It does not mean setting a long run of loose trusses and planning to straighten everything later. The first truss receives special attention. Before succeeding members are erected and secured to it, the first truss must be plumbed, connected, braced, or guyed against shifting. I do not count two workers holding it by hand as the required restraint. Their grip can change, wind can act on the broad truss surface, and the next suspended member can introduce movement. Imagine a crew racing an incoming weather change. The first gable truss is sitting on the plates, and the crane is ready with the next piece. The shortcut is to let workers steady the first truss while the second truss arrives. The supported consequence chain is simple. The first member can shift laterally. The next member adds contact and movement. Temporary spacers can pull succeeding trusses with the first. What began as a time-saving shortcut can become a multi-member overturning event. I want to keep that consequence realistic. A shift does not guarantee a total collapse every time, but the condition creates the exact buckling and overturning hazard that progressive bracing is meant to control. The supervision decision is made before the next pick, not after movement starts. Temporary bracing also has to follow the approved erection information for the system. I do not invent a universal lumber size, spacing, or ground brace pattern from memory. Truss geometry, span, height, wind exposure, erection method, and the approved submittal package all matter. The field rule is to use the specified system and keep it effective as the work advances. The first truss memory connection is the first domino. If the first standing member is loose, every following connection can transmit movement back into it. If the first member is secured against shifting and the run is braced progressively, the crew is building stability instead of borrowing it from human hands. Temporary erection bracing and permanent individual truss member restraint are not two names for the same thing. Confusing them can produce a roof that survives erection, but is missing a restraint needed under service loads. California Building Code, Section 2303.4.1.2 ties permanent member restraint to the approved truss design drawings. The comparison table on screen shows the clean distinction. Temporary bracing is installed during erection to control lateral instability, buckling, and overturning, while the roof system is incomplete. Permanent individual truss member restraint is installed where the approved truss design requires it, and remains as part of the completed structure. Some long web members carry compression. A compression member can bow sideways before the wood itself reaches the force it was designed to resist. The specified lateral restraint shortens the member's unbraced length. Diagonal bracing, or another approved method, then transfers that restraint into a stable part of the system. That is the practical effect supported by the truss design requirements. I do not assume that roof sheathing automatically replaces every permanent restraint node. I read the truss design drawing. If the drawing identifies a member that needs continuous lateral restraint and associated diagonal bracing, that information stays in the work until the approved design says otherwise. The sequencing distinction matters too. Temporary bracing must function while the crew is erecting. Permanent restraint must be complete as part of the finished framing system. There can be overlap in materials or timing, but the purpose and controlling instructions remain different. Removing every temporary piece does not prove the permanent system is complete. Leaving random temporary pieces in place does not prove it is correct. A useful inspection question is not merely, is there wood across the webs? I ask whether the right member is restrained at the right location, with the required connection and bracing shown by the approved documents. That keeps the check tied to design rather than appearance. Field alterations are not limited to saw cuts. The code boundary also covers added loads. California Building Code, Section 2303.4.5, and California Residential Code, Section R802.10.4. Do not permit loads to be added to a truss member without verification that the truss can support them. That means I supervise more than framing. Heating and cooling equipment, piping, suspended equipment, added roofing, or insulation beyond the design assumptions can create concentrated or distributed loads that were not part of the original truss calculation. The fact that an item fits in the attic does not prove the truss was designed to carry it. Imagine a subcontractor who wants to hang a heavy piece of equipment from the bottom cord because the location is convenient, and the cord looks straight and substantial. The visual impression is not a load check. The bottom cord may be carrying tension and sealing loads under a specific design. A new hanger can introduce a point load at a location the design did not account for. The field response is to verify the proposed load against the approved truss information and obtain design confirmation when the load is not already covered. The answer may involve a designated panel point, supplemental framing, a different support path, or a redesigned truss detail. I do not invent which solution applies. That decision belongs in the approved design information. This is where coordination saves both structure and schedule. Mechanical, electrical, plumbing, roofing, and insulation scopes should be compared with truss geometry before rough work reaches the conflict. A planned chase or supported equipment location is much cheaper than an unauthorized cut, followed by shoring, engineering, repair materials, reinspection, and delayed concealment. The connected construction principle is access before concealment. Truss conflicts are easiest to solve while documents, framing, and trade routes are visible. Once ducts, wiring, ceiling backing, and insulation crowd the space, the same design issue becomes harder to identify and more expensive to correct. Large trusses add a separate inspection layer. California Building Code, Section 17.05.5.2 uses two thresholds that are easy to confuse because both use the number 60, but they measure different things. The decision matrix on screen separates them. An overall truss height of 60 inches or greater triggers special inspection to verify that permanent individual truss member restraint is installed properly. A clear span of 60 feet or greater triggers special inspection during construction of the temporary installation restraint and bracing in accordance with the approved submittal package. The memory connection is inches for height, feet for span. Height points to the tall truss profile and the permanent member restraint check. Span points to the long reach across the building and the temporary erection bracing check. A truss can meet one threshold, both thresholds, or neither, so I do not combine them into a single 60-unit rule. The important supervision step happens before erection. I identify the truss dimensions from the approved documents, determine whether special inspection is required, and coordinate the qualified special inspector with the erection schedule. Discovering the requirement after the bracing is hidden or removed defeats the point of observing the work that must be verified. I also keep the special inspector's role separate from the truss designer's role. The special inspector verifies that the specified work is installed as required. The special inspector does not create an alternate bracing plan because the crew prefers a different setup. Design changes still return to the proper design authority. These thresholds are testable concepts based on the published CSLB study outline because they connect roof framing, shop drawings, field inspection, and safety coordination. I treat them as practical scheduling facts, not trivia. They affect who must be present and what must remain visible. Fall protection runs alongside structural stability. During residential-type framing activities, employees walking or working on top plates, joists, rafters, trusses, or beams must be protected from falls when they are 6 feet or more above the lower level. The source is Title 8, Section 17, 16.2, subsection E, paragraph 1. Acceptable protection may include scaffolding, guardrails, safety nets, or personal fall arrest systems, depending on the work and the applicable requirements. A site-specific fall protection plan is not a casual substitute because conventional protection feels inconvenient. The employer must establish that conventional methods are infeasible or create a greater hazard before relying on that limited approach. I keep two hazards separate in my supervision. Fall protection keeps a worker from falling from the framing. Erection bracing keeps the framing from buckling or overturning beneath the worker. A harness does not brace a truss, and a braced truss does not eliminate the worker's fall exposure. Both controls must be addressed. That distinction matters during crane picks. The crew may be focused on taglines, connections, and getting the member plumb. I still verify the work position, access method, fall protection, and structural restraint as coordinated parts of the lift. Rushing one control to complete another is not a sound sequence. My field memory check is short: documents before installation, inspect before lifting, secure the first truss before the next one, brace progressively, install permanent restraint exactly where the approved truss information requires it. Do not cut, drill, splice, or add unverified loads. Bring in the registered design professional for repairs or changes. Coordinate special inspection at the 60-inch and 60-foot thresholds. Protect workers from falls at 6 feet or more during the covered residential-type framing activities. There is an audio practice quiz built specifically for this episode on roof truss drawings, bracing, and field alterations. It is audio-based, so the questions are read aloud and you answer by tapping, which is made for the way you are studying while driving, working, or moving through the day. Go to the description below this video. You will see a link that says Pass the CSLB. Tap it. It will take you straight there. Comment below with any questions about anything I covered. I read those questions because they show me where the material is still getting in the way. Subscribe so I can help you stay on track through every episode until you get your license. I know you are fitting this study time around real work, and I am genuinely glad to be in your corner.